Okay, let's get back into Turing machines. So, has anyone thought about how to use a Turing machine to solve this problem? Well, let's think about it for a second. So, the way I like to think about Turing machines is think about the best case, about if we get an input that is the one that we want, how do we actually do the check there, and then worry about the other cases later. So let's just say we have a 0, 0, 0, $, 0, 0, 0, and then blanks afterward. And the tape head is pointed at the beginning of the tape. So how do I check if it's same number of zeros on both sides of the $, but I can only move left or right, one cell at a time? How could I check that?
Compare one at a time.
Yeah, well, let's see. If I just compare one to another, that could be good. But if I just move to the right and then look for a 0, if I just move this tape head over to here, then how do I know that I checked a 0 on the left side? Right? I don't know if I checked that. So one suggestion in the back is, how about let's just write an X when we've looked at a character on the left side, and what about the right side? Yeah, put an X on the right side too to denote we've seen an X on both sides. Oh, sorry, we've seen a 0 on both sides, which means that we can move on to the next set of zeros, and then the next set of zeros, until we reach the $sign on the left side. So, for example, we're going to start here again, but now we're going to cross off, put an X in the first cell where the first 0 is, and then what do we want to do? Yeah, move to the right until what? To the $sign, and then what? Look at the first non-xed 0 on the right side. But we haven't xed any zeros out yet, so we're going to be coming over here and then say, oh yeah, there's a 0 there. What should I do with it? X it out. Good. And then, so now the tape head is on the right side. What should I do? Move right. Well, I could move right, but what's a simpler way to do it? How about I move left all the way over to the first unmarked 0 on the left side, and then do what? Do the same thing, right? Find the first unmarked 0 on the left and right side, mark them, and then march in tandem across both sides. So if we did that, so the tape head is currently on the right side. If we move left, how do I know I found the first unmarked 0 because I can only see one character at a time? Oh yeah, I find an X. If I find an X on the left side, what should I do? Move right. So now I definitely am pointed at the first 0, if there is a 0. Okay, so then we're going to do the same process again, cross that second 0 off with the second 0 on the right side. Then go back, find the first 0, which is this one, X, X. And so now I want to discuss this situation right here. So now I'm pointed at the very last what was a 0, and then now we're going to go back in the same way that we did before. Which character am I going to stop moving left on? The third X right here, right? And then what does my finite control tell me to do? Move right, because that's what we did before. Okay, so now we're pointed at a $sign. Success. Or is it? What if this had a 0 on the right side? See, now we got to start working in the corner cases. What if we had a 0 on the right side? It'd be a failure. How do I check there's a 0 over there? Just move right across the second set of x's until what occurs? Well, what things should I see? If I see a blank, what should I say? This is success, right? If I see anything else, other than an x, obviously, reject, right? So if I see a 0, I reject. If I see a $sign on that side, why should I also reject? Right, it's not the language, because the language says there's exactly one $sign in every single input. Okay, so now does everyone understand the idea behind this machine, what it's supposed to do? So one more thing. So are computers deterministic? Do they do the exact same thing every time? When provided the same input? Yeah, they do the exact same thing every time. So what we want these machines to be are also deterministic. So if I feed this input to this machine several times, it'll be the exact same answer no matter what. Okay? So we want TMs to be deterministic. We will talk about non-deterministic Turing machines, but we'll stick with deterministic because it's easy to work with. Okay, so now we're going to make a state diagram for a Turing machine to have this language. So if it's presented an input of a 0 to the n, $0 to the n, it'll say accept or yes. And if it's any other kind of input, it'll say no or reject. Okay. So the way that we're going to make states is they're going to be these circled name things. So this state is called Q0. I may have another state called Q1, Q2, Alabama, Arizona, lots of different state names, right? So these states will have a certain name attached to them. And then we'll draw arrows between states to determine if I'm in this state and a certain thing appears on the tape, I'm going to transition to this other state. So remember for our simulation from before, if we saw a 0, we're pointed at the left side, what should we do first? Right, so we take a 0, we saw a 0 in the tape, we put an X there, and then what did we do with the tape head? Which direction? We moved right. So we need to be able to go to a different state which corresponds to, now we're going to transition over to the other side of the input. So this state says Q0 represents, we're on the first unmarked 0 on the left side, and now we need to decide what to do. So the transition we're going to have here says, we read a 0 on the input, we're going to write an X there, and move right. So the way to denote that is 0, we saw a 0 on the tape, comma, X, the symbol to be written, and then arrow R. So R represents right, and L will represent left. And by the way, I have no idea why states are called Q sub something. That's just a bad accident back in the 50s when these things became formalized. Okay, so Q1, that's the state that represents, now we're zooming across the tape to the second half. But when we're moving across the tape, we're going to bump into some character, which is the $sign. So Q1 is going to represent moving across the zeros on the first half. So what things should I see over and over again until I see a $sign? Zeros. So I don't know how many it's going to happen, right? So I need to make what is called a self loop on Q1. So this just means stay in Q1 until you encounter a transition that goes elsewhere. So Q1, this transition says, I see a 0, I'm going to write a 0. So so good exam question. So make sure to write it down. Turing machines, do they always write or no? So we may consider a model where Turing machines don't always write, but here they always write something. They may write the same character down, which it will in this case, but they always write something. So I could write 0, 0 goes to right, because I see a 0, write a 0, and move right. But there's a nice shorthand because this sort of thing going across the tape happens all the time. So the way we're going to write that is 0, arrow right. To mean we're not going to change the contents of that cell on the tape. So if we see a 0, just zoom past it. Write a 0, but zoom past it. And then which thing am I going to hit? $, which means I must transition to a different state. So, but am I going to change that $sign to something else? No, because I need that character there. So again, we're going to have $sign goes to right. Surprise, the next state name is Q2. Okay. Oh, I did it backwards there. Okay. What thing am I going to see initially on the second half? Well, the first time I'm going to go there, I'm going to see a 0. And what am I going to do with it? Write an X. But the second time, what am I going to see first? An X. But then I need to be zooming past what to get to the first unmarked 0? X's, right? I may have 0, like this first, the transition for Q1, the 0 goes to right. I may do that self loop 0 times. But if I need to do that transition, then there is one for me. So for Q2, there may be 0 X's on the right side, but if there are any, I need to zoom past them anyway. So I'm going to have a X goes to right there. Okay? Great. So now we're zooming past the X's. What thing should I see next? 0. And then, so when I see that 0, what am I going to do with it? Write an X, and which direction this time? Left, right? That was not meant to be a pun. So once we see a 0, we write an X and move left. I can't go back to the other states because the state, what I need to do next is zoom past backward, going left, to the beginning where I can do this process all over again. So I need another state or set of states to handle going backward. So initially, when I'm moving back, what am I going to see first? X's, right? Before I see the $sign. So I need to have $sign goes to left. Good. Involuntary participation. Okay. Oh, no, sorry. Should have corrected me. X goes to left. What should I see once I zoom past all of the X's on the second half? $sign. I should see a $sign, and which way? Left. And of course, not change what was there. Okay. Well, I can't go back to the Q0 state because I still have stuff to cross in order to get to the first unmarked 0 on the first half. What am I going to see along the way before I find the first one? Zeros, not X's, because the X's are on the prefix part. Okay, so here I need to do 0 goes to left. I'm going to be zooming past zeros. But now, once I zoom past all the zeros, what should I see? X. And then what should I do once I see that X? Move right. Oh, where should I go? What state should I go to after I move right? Go back to the Q0 state, because that handles moving right and doing this whole procedure all over again. So Q4 is going to go all the way back to Q0, thankfully. X goes to right. Okay. Is that it? What have I forgotten? What is the main thing I've forgotten? There's a lot I've forgotten. Oh, what was it?
Mine's different. I was going to say if you didn't pass in any zeros.
Well, that's actually a good point. And actually related to what I was going to say. If I had 0 zeros, what is the first character I should see? $sign. So in Q0, I need to handle the case when I see a $sign. But exactly the same question. When I do this process going back and forth all over, and I go back to find the first unmarked 0, we had this one case where I point to the $sign once I move right one position. So I need to know what to do. So what state am I in when I move right for that first time? When I zoom past all the way going left and then I move right one. What state am I in? Q0. Oh, so I need to know what to do in Q0 when I see a $sign on the tape. So I need to know what to do when I see a $sign on the tape. Well, which direction should I go for sure? Right. Well, I can't immediately say accept or yes or whatever, right? I need to do this final check at the end to see, did I forget some zeros on the right side? So what should I do? Yeah, but in terms of a Turing machine, what is it going to do? Yeah, move right until hopefully I see what? The blank symbol. And if I'm unlucky, I see a 0. Okay, so we need to handle that. So let's make a Q5. And what should Q5 do as a transition? Should it self-loop? Yeah. And what should it do on the transition? Help me out. If it's an X, move right immediately. Good. Oh, no, because we ensured that we only marked one on either side.
Right, but if you just have an X coming in from the input?
We're going to have two alphabets. One that says what can appear on the input and what can appear on the tape. Here we're going to insist the input be only of zeros and $signs. If it's not that, just stop computation immediately. So yeah, that is important to distinguish between these. Other questions? Okay, so once we're in Q5, what should I hopefully see? A blank, and does it really matter what direction I move? No, so is it ever safe to move, is it always safe to move right on the tape? Yeah, because there's always more tape to the right of you. Is it always safe to move left? No, because we have this one-way tape thing, and if I'm at the beginning of the tape, so there are different models here, but we're going to adopt the model that if you move left off the left-hand end of the tape, computation stops immediately because you're doing a thing that's illegal for a Turing machine. Another type of model that you could consider is it just bounces off the left-hand end of the tape, but stays in the first cell, but we're going to adopt the model that it just stops immediately. So, but I'm always safe to move right. That's always okay. So here we're going to have blank moves right. And if that's true, we saw blank right there and no zeros, what should I say? Success. Great. And should I stop or should I keep going? Now I stop. So I know for sure I'm in a situation where I can stop. So we're going to have a special state for that when I say yes, called Q accept. And this will be introduced in the formal definition too, but it's good to have it here. Okay, is this clear? Are there any questions about it? So note how we actually built this machine. We built it in stages. The idea that we happened to have the case where we're moving in the left half, then handle when the dollar sign was there, then handle the second half, and then moving back left, and then finally the case when we ran out of zeros on the left half, what we needed to do there. Is this machine done? No. What did I forget? What if I'm in Q5 and I see a 0? What if I'm in Q0 and I see an X? Sounds like a problem, right? What if I happen to see an X in Q0? Is that something that I want to happen? No. So should computation immediately stop right then? Or when we're in Q5 and we see a 0? Right? In those cases, we know that something wrong will happen. We should stop and say no immediately. So, and of course, look at all the other transitions that we left out. Say for Q2. What if Q2 we saw a dollar sign? Right? In the case when we had two dollar signs on the tape, right? That could happen. So we need to be able to handle that because we want Turing machines to be deterministic. Okay? So a common way to handle this is say unwritten transitions go to a special state for handling the no case instead of the yes case is go to Q reject, which is a state. So the Q5, you see a 0 transition will go to Q reject. Any questions about that? And so because these diagrams can be quite complicated, if you include every single transition, this is always a good thing to do. If you state this, you're okay in not including some transitions, because handling every single case is quite cumbersome. All right, any questions before we go on to formal stuff? Okay, well, we could, of course, talk about these machines and draw pretty pictures all day long, right? But if you have a different intuition about these machines than I do, then something wrong could happen, right? Because as we'll find out, English is an awful language for formal writing. So we want to specify these machines in a formal way. Yeah.
So I think that's for Q2 to Q3. The answer would be accurate. I think it just would be 0.
I'm not sure what the question is.
For state Q2 to Q3.
Mm-hmm.
So you write 0 for X and now.
Mm-hmm.
I think it's just the 0.
0L, but I'm marking the second 0 on the right side.
If we are at like Q2,
yeah. Mm-hmm.
the X version you go right.
It goes left because we got to transition back to the start.
So you have the step loop for X to right Q2.
The self loop at Q2 is X because if we're in this case where we're here. And then we're back at the beginning where we mark off this first 0. We got to mark the second 0. So we need to be able to go over to there. So Q0 handles the case where we just saw that first 0. Then it moves right until it sees the dollar sign, moves right, zooms past the already marked X's on the second half to the first unmarked 0. which is this third one in this case. And then Q2 has a self loop zooming past all those x's on the second half until it transitions to Q3 with when it sees that first unmarked 0. Does that make sense? Or I'm not sure what the question is. We can talk offline if you're still confused. Yeah.
I saw that in other examples that you showed a 0 and then an arrow and then like X and then a comma and then right.
In the lecture notes?
I'm not sure where I saw it.
Yeah, so this stuff has every single possible combination of symbols you can ever imagine. So the most common one is this one, where the reason why it's written this way is that the arrow represents, that's the direction we're going to go, and pointing to the L or R that we're actually going to do. And the work that's being done is on the left half of the arrow. That's the reason. At the very end, we're going to come across a model where we have the comma and the arrow flipped. So it's where you have an arrow first, then a comma for a different model, for a completely different reason. Yeah?
The self loop, where it writes to itself, do you want us to keep it like that, or do we write like X, comma, X, and then arrow?
Either one is fine, but because you're going to be doing the transition that corresponds to not changing the symbol happens so frequently that I highly recommend doing it that way. But you're absolutely welcome to do it the old way with the same symbol twice. But either one is okay. Any other questions? Okay, so let's talk about formal things. So, definition. A Turing machine, and it's a pain to write that over and over, so I'm going to abbreviate it as TM. Not trademark, but Turing machine. Is a, and then something that I'm going to fill in later, where, so think of the things that we need to be able to specify. What is the thing that's most evident in the picture that we had here? States, right? So we need a finite set of states because we had this finite control. So Q is a finite set of states. And then now we need to, the second thing that's most evident in the picture is what is actually presented on the tape. So going back to the question that was raised earlier, where we had this confusion about what was actually on the tape. So if we specify, here is exactly what characters you're allowed to put on the input, and here's precisely what characters you can put on the tape, that are not necessarily part of the input, that would need to be specified. So sigma is a finite input alphabet. And for the tape, is gamma is a finite tape alphabet. So for the machine that we just made, what is the input alphabet for it? What characters can I put on the input? Not necessarily just the tape, but only of the input. 0 and $. Yeah, because I have to have those two characters. I don't need any more. So sigma, so I'm going to put a little thought bubble here. Sigma in that case is 0 and $. Gamma is the set of all characters that can be placed on the tape anywhere. Okay? What characters can I put on the tape anywhere? Well, obviously, 0 and $, for sure, because I got to put the input on the tape. But what else can I put on the tape? X and blank symbol, right? So we need to be able to handle that as well. So gamma in that case is $, $x and the blank character. Any questions so far? Because this is not the crazy part yet. All right. Let's see. Of course, the tape alphabet can contain many more symbols than what is presented in the input alphabet. But what character can we not put in the alphabet, the input alphabet at all? The blank symbol. Why shouldn't we put the blank symbol in the input alphabet, but only the tape alphabet?
Outside of the tape.
Right. So if we, let's just say that I provide, if I do allow the blank symbol in the input alphabet, and I present an input to you, and you see the entire tape is full of blanks, and you say, well, the tape is completely blank. And I told you, no, I provided you 10 blank characters. Right? How would you tell? Right? Because all the blank characters are the same. So we need to say that the blank character is not in the tape alphabet, the input alphabet. But, and also, the blank character is always in the tape alphabet. That always has to be there. But what other relation between the input and tape alphabet can we say? Right, the input alphabet is a subset of the tape alphabet. Why is that? I actually already said it, but right, the machine has to have the input on the tape already. So the input alphabet definitely has to be a subset of the tape alphabet. So sigma is a subset of gamma. By the way, if you can't read my atrocious handwriting, please let me know. My feelings won't be tarnished. Okay. Okay, we have all these state things, and we have, we're going to describe the transitions in a second, but we need to talk more about the states themselves. Well, let's see. One thing I didn't talk about before is, what is this arrow coming in from nowhere? What is that indicating?
Start.
Oh, it says start there. Does that mean I can start in Q2? I mean, I can put the arrow there, but in this diagram, can I start at Q2? No, right? So I need to specify, what if I didn't include that arrow coming in from nowhere at all? Do I know where to start? Well, you can just say, start at the state called Q0. Is there always a state called Q0? What if I call them Alabama, Arizona, Kansas, all great state names, right? So how would I know what state to start at? So we always will specify one state that's the start state. So we're going to give it a name, which is Q0, which is a member of Q because it has to be a state, is the start state. And just because if I give you two state names, that could correspond to the same state. Okay? Just because they have different names, they could be the same state. We can actually do an example of that. But what other states must we have in a Turing machine? Well, right, we need this accept and reject thing because I need to know when to stop. So we need to have two states, Q accept and Q reject in Q. I need to have those states in there. What else should we insist about Q accept and Q reject? Can they be the same state? No, because I need to differentiate between when I want to accept or say yes versus when I want to reject or say no. So we need to say that Q accept is not equal to Q reject. So this is actually what I was just saying about different state names being the same state. If we didn't say that, then we could have a state that's both the accept and the reject state simultaneously, which obviously makes no sense. Okay, does that make sense? Okay. Could Q0 be Q accept? Yeah, certainly. What language would that be of that machine? It always accepts no matter what the input is. It's sigma star, or whatever the input alphabet is, star. Okay, are we done with Turing machine? The description of a Turing machine, the formal model. No, what have I forgotten? Transition. Well, let's see. What did we need to know about? I start in this state and I need to get to this state, which means I got to do what three things? I got to look at the current state, which is the state over here. That's one thing. What else do I need to do? I need to first read what thing I'm looking at. If I'm at Q0, there's a difference between if I see a 0 or a dollar sign. So I need to look at what's in the tape first, but then what do I do? Knowing those two things, what do I do? Well, I must write something, some character in the tape alphabet. What do I do with the tape head? I move left or right, right? What else might I do in terms of states? I may stay in the same place or go to a completely different state, right? I may do a self loop, may do a completely different state. But I'm always going to go to some state in Q, the set of states. Okay? Let's see. So the transition function, as it's called, is going to take the state that we're in, the thing that we read on the tape. It's going to tell us which state to go to, what thing to write down in that cell, and which direction to go. Does that make sense? Okay. Cool. So delta is the transition function where delta takes what two things? A state and a not necessarily input, but something on the tape. Oh, do we have something that tells us what things can go on the tape? Ah, the tape alphabet. Do we have something that tells us what the states are? Ah, the set of states. So we need to have an ordered pair starting with something in Q with something in the tape alphabet. So Q times cross product with gamma, the tape alphabet. So the digital and among you will already see a difference. I'll come back to that. So Q cross gamma, and that's going to give me a state, something to write, and which direction to go. So that's going to be an ordered triple. Q cross, because that's a state, cross something in the tape alphabet, cross either what two things? Left or right. So from the set LR. Okay? What else do we insist about this transition function? Not what's in the definition, but what else do we insist? Can I have, say, go back to our example. Can I have Q0 with seeing an X not defined to go to some state? Could I have that? No, I want these machines to be, the magic word, deterministic. Oh, so we need every single pair in this left-hand side to be defined. Anyone know what that's called? a total function. All this means is that no matter what state and symbol you give me, there's some transition to apply. Okay? And in fact, there's exactly one because this is a function. Okay? If I had this diagram above with the missing transitions, is this a Turing machine? No, because the transition function is not, magic word, total. Good. Which means, so I need to have all, if I have all the transitions in there, then it actually is a Turing machine. Any questions on that? And you may think, so now I'm going to come back to the difference on the notes. You may notice, okay, let's say I have all the other transitions there. Does Q accept as a state, right? Do I need to include if I see an X there or anything? Do I need to include that? No. What happens when I go to Q accept? The machine stops, no matter what. So I need to disregard when I go to Q accept any transitions coming out of there. Well, what about Q reject? Is that the same story? Yeah, it's the same story. So the more common way of writing this is put a Q bar there, and Q bar is Q without, so that's set minus, Q accept, and Q reject. So that's where that terminology comes from. I think I got that right. Yeah, so that's exactly the precise formal definition of a Turing machine. But it mimics the intuition that we had. Any questions about that?
Why is the input alphabet used at all?
What's sorry?
The input alphabet not used in delta at all?
Because I need to be able to handle any symbol on the tape. Because immediately right from the beginning, the input's going to be destroyed anyway, most likely. So let's just handle the general case where it could be any tape symbol. Any other questions? Okay. Well, let's see. If I look at this machine and look back at the work that we were doing on the tape above, we were just looking at, okay, if we see this X, then we're going to transition over here. I drew a dotted line and we crossed out this X, then I erased the dotted line and we went back here. And so is that a formal way to specify that we are computing this? It doesn't seem very formal, right? It's just a pretty picture where you're having some tape and I have some X's there and dotted lines, but that's not really formal, right? So we need to be able to specify what a computation of a Turing machine is. So for example, if you have a friend who is not very sure that you're actually running your Turing machine, because you obviously all have Turing machines, right? If your friend is not sure that you're actually running your program, right? Which may happen. What you want to do is, how do you convince your friend that you actually ran that program? So how would you convince your friends that you ran some program? Well, what you can show is the stack trace over time, right? You can just stack trace at this moment, stack trace after this instruction, after this instruction, after this instruction, and it carries the entire way through. We're going to do the exact same thing here. So we're going to specify what are called configurations of the tape at any given point. And then we can use configurations to say, here is a way to define how a Turing machine computes something. So a configuration of a Turing machine in, let's say, state Q and has tape contents let's say S1 through SK. There's actually an issue with this, but I'll address it in a second. Let's say it has those tape contents and it has state Q. And let's say it's looking at state I is the string S1 up to SI minus 1, QSI through SK. All this is an encoding of the Turing machine at this snapshot. I take a snapshot of this machine, and I can recover all the information about the machine. But so this actually kind of relates to your first question on your problem set. If I give you that right there, can you start the Turing machine back up right where it was before, using that string as if I give you that string? Could you figure out what the Turing machine was doing? Is this a valid encoding? Well, let's see. Could you figure out which state you're in? Well, how many states are in this string? There should be only one, because the SI things, those are the tape symbols, not the states. So what's the only thing that's a state there? Q. So you just look and say, oh yeah, there's the state right there. So you can recover the state. Can you recover what things were on the tape originally? Yeah, just drop the state that was there, and then now you have the tape that was there. Pretty nice. Can you recover where the tape head was? Yeah, so the way you recover it here is you say, oh yeah, here's the state right there. Look to the character in the string to the right of you. That's the character you were looking at right before me, or right before you just stopped the Turing machine. Okay, so here it just says you were looking at SI right before you stopped the machine. And so now I can recover which character I was looking at, what tape cell I was looking at. So this is a valid encoding. Okay? Any questions about that? Yeah.
Okay, so are you saying you could go backwards to the original input from this?
Oh, no, you can't. That was a mistake on my part. Go back to right before I stopped the machine.
Okay.
Yeah, that's a red herring. Yeah.
How do you know the one you were looking at is the one to the right?
That's the way the encoding works. So I need to put so I'm encoding a lot of information in a short string here. It's just if you're given this string as input, you look for where the state is, then look at the character to the right of that. That's the character you were looking at right before you stopped the machine. Like in a program, if you look at the stack trace, you can see, oh, if I have the state of the computer and I put it right here in the stack trace, I look to the right of where I was, that is the exact function call in the exact line that I was in right before I stopped the program. It's exactly analogous here. But any other questions about configuration? Okay, so let's actually define computation. So the computation idea is just, I give you the starting configuration, which is right when I start up the machine, and I'm going to make a whole bunch of configurations in order, and one is going to be derived from the last one via a single transition. So I can look at where the differences are in adjacent configurations, and I can say, oh, yeah, that's exactly this transition that occurred over here that caused this to occur in the next one, and then the next one, and then the next one. And then we're going to say that the Turing machine accepts an input if the last configuration at the very end lands in the accepting state. And it says no on the input if it ends in the rejecting state. So a computation then of a TM, let's call it M, on input, let's call it W, is a sequence of, I should say finite here, finite sequence of configurations. So I'm going to short it to configs because I hate writing long words, as you might expect. C0, C1 up through, let's say, CS. So these are the configurations in order where C0 is the starting config. And then we'll get to rest in a second, but I'm going to ask a few questions about this. When I start the machine up, what state am I in? The Q0. Let's see. Let's say I present this same input every single time, this string W. If I present this same string every time, what is the starting configuration? What character am I looking at? The first character of W, right? So, in fact, the config itself is C0 is Q0, W1, W2, let's say Wn. So I'm looking at the first character. If I feed you the same input every single time, does this starting configuration ever change? No, because the starting state is exactly the same, and the input is exactly the same. So in fact, that's why I say the starting config here, because there's exactly one config if I fix a particular string. Well, let's see. Since this machine is deterministic, for C1, which will be derived from C0 after a transition, could there be more than one possibility of the next configuration, or will there be exactly one? One, because the machine is, important word, deterministic. Good. But that handles all the way through, right? So if I look at CI, let's say for instance, which is derived from CI minus 1, the previous configuration, is CI, is there only one possibility of CI to occur? Yeah, there's only one to occur because the machine's deterministic. So let's say CI is obtained from CI minus 1 for all I. And this obtained from phrase means, we're going to paraphrase this as yields. So CI, sorry, that's not quite right. Another way to say this is CI minus 1 yields CI. I had the wrong direction. So yields goes in the forward direction here. So let's say that the state is Q and the tape contents are S1 through SK again. At position, and tape head as before at position I. And then let's see what happens. So let's say that if CI minus 1 is S1 through S minus 1, Q, actually it has to be this, through SK, because that's just the information that we assumed. Well, there are three things that can happen. Well, we could move right at this point, right? So let's say that we move right and write B to the tape. So in this case, CI will be what? Will that SI still be there if we just wrote a B? No. So the SI is going away and becoming a B. What character am I looking at now if we moved right? We look at SI plus 1. Good. So CI now is same I minus 1 at the beginning, but now it's a B because we moved right and wrote a B. Let's say we go to state Q prime. Then we're now in state Q prime, looking at, no, that's right. Looking at SI plus 1, going through SK.
Question on.
Yeah.
Is the I subscript to C the same as the I subscript to the S's? Is that...
Oh, that's quite unfortunate. Thank you for pointing that out. It should, what was pointed out is correct. The subscript should be different. So let's just say position J here, and then we can change the subscripts here to J. It's not really that important, but it's just to be precise, which is always important in this class. All right, good. A special case of this one, what if we were at same thing, but J equals K here? Which means we were looking at the last character in the tape contents, and we moved right. So now what happens? What thing am I going to look at next? A blank character. So in this case, now we're going to put the blank character into the configuration. So in this case, CI is going to be the same thing as before. B, Q prime, SJ plus 1. Oh, no. That should be this. And it should be a blank character there. Just to note, if we go too far, we're going to put a blank character in the configuration. That's all we're going to do. And the only other case is if we move left, right, a B, go to state Q prime, sorry. Well, CI is going to be something else. Well, the SI definitely is going to change to a B now because we always read a B there. But now we move left. What character am I going to look at now? S of J minus 1. Good. So instead of looking at Sj now, we're looking at Sj minus 1. So here we have S1 through Sj minus 2. Let's see. Q primed Si minus 1, because we haven't changed, should be J minus 1, sorry. We haven't changed the J minus 1 yet, but we changed the Jth one in the transition. So this is B because we changed it, and then Sj plus 1 through Sk. So I know it's absolutely horrible, but one thing that you should be thinking about as you're doing this sort of thing is that you should write down what you're trying to do. So we're trying to formalize the notion of computation here. And so we're just saying, here's the configuration at the start, and you follow the rules of the transition function as we go along. That's all we're doing. And then we say a computation is accepting if the CS, the last configuration, contains Q accept. I still have 3 minutes. I will use all the time every single lecture, I promise you. the goodness of the class. All right, so then a computation is rejecting if CS contains Q reject. Okay, so if we land in Q accept at the end, we say that's an accepting computation, right? Or we accepted the input from the beginning, and rejecting if we don't accept the input. Then we say the language recognized by this machine M, and we're going to denote it L of M. So this just means language of this machine M. And we're going to use this notation all throughout the class. So L of M is just all the strings W in sigma star. So in the input alphabet, where M has an accepting computation on that string. So in other words, it accepts the string. Has an accepting computation on W. We still have enough time. A language, L, is Turing recognizable, or we just shorten it to be just recognizable because it's evident that it's by Turing. If some TM recognizes it. So if you have like the 0 to the n, $, 0 to the n, the one we came up with, we made a Turing machine for it. So is it Turing recognizable? Yes. Good. So further, we have a language, L is Turing decidable, or just decidable, if some Turing machine recognizes it and the TM always halts. So the machine always stops. So here's another great exam question. Can a recognizer, so a machine that has that recognizes some language, can that machine, a recognizer, run forever? Not a decider, a recognizer. Yes, it might run forever. Can it run forever on the strings in the language, which means it has an accepting computation on them? Can an accepting computation be infinitely long? No. So in fact, for the Turing recognizable languages, the machine will always stop on the strings in the language. Okay? Any last minute questions on that? Yeah, so I know it's over time. If you need to go, that's fine with me. What I said was a Turing, a recognizer, so not a decider, a recognizer, it has to halt on the strings in the language. So whatever language we have, then the machine has to stop on those strings. It might run forever on the ones that that are not in the language, that it doesn't have an accepting computation for. But if it's a decider, whether it's in the language or not, it must stop, always. So we'll come back to that next time. I have office hours for an hour after this, so I'll see you all on Monday. Sorry I went over time.